guys, Miss Venable here, bringing you a presentation on electron dot diagrams. We will look at atoms and we will look at ions. We're going to not include polyatomic ions just yet. Those will come later, and we're really never going to do dot models for those. Okay, so what is an electron dot model? Well, it's a quick way to kind of help us visualize what's going on with valence electrons. Remember, these are the electrons in the outermost energy level. They're the electrons that are involved in chemical bonding. So it's really important that we know how to represent the number of valence electrons correctly. We're also going to look at how those electrons might be lost or gained in order for the atom to form an ion. So the diagram is basically going to include the symbol for the element. In this example, we're looking at argon, so the chemical symbol is Ar, and that always goes in the middle of the dot diagram. And then around the outside, there are 4 different positions where you're going to place dots that represent valence electrons. So remember not to do all the electrons, just show the valence electrons. Okay, so here are the 4 positions. You can do left side, top, right side, and bottom. And so in this presentation, we're going to go over how do you figure out how many dots to put in your model and where exactly do you put those dots. Okay, so let's talk about how many dots. Well, in order to know how many dots, you need to know how many valence electrons. So don't look at all the electrons, which would be the atomic number. Look at Roman numerals. Okay, Roman numerals always tell us how many electrons. So across the top of your periodic table, you have group 1, group 2, and skip those transitions. And then you have group 3, 4, 5, 6, 7, 8. And basically, those Roman numerals tell you how many valence electrons those atoms are going to have. So I've placed those Roman numerals at the top here for you guys to see. And if you look on your periodic table, there will also be the letter A afterwards, after that Roman numeral. And that means that those elements are representative elements, which means all of the elements in those groups follow that rule. The ones that you don't have a known number of valence electrons are a little bit more challenging. Okay, so if you look at the transition metals here, those are called group B elements. And also in the bottom down here, some of these poor metals. Okay, they don't have just one possible number of valence electrons. They actually have what we call variable oxidation states. They have the ability to promote electrons from lower energy levels to the valence energy level, and they can do it in different ways. So what we're going to do for those transition metals and some of those poor metals is they're actually going to tell you what the Roman numeral is when they name it. So like they might say lead, Roman numeral 3. I would be 3. And then you know that it's got 3 valence electrons. So they kind of have to tell you how many valence electrons when they give you the name of the element. Alrighty, so there are a few exceptions, okay, to this rule. So there's no exceptions in group 1. All the group 1 elements, the alkali metal family, all have 1 valence electrons. No exceptions in group 2, okay. The transition metals are largely variable, but there are 3 exceptions, and that is cadmium and zinc. They're both 2. They both have 2 valence electrons, and they're not variable. Most of the transition metals vary, and they have to tell you a Roman numeral, but they're not going to do that for cadmium and zinc because they expect you to know it's always a 2 valence electrons. And then silver is always a 1. So it always has 1 valence electrons. It's not variable. The other exception is helium up here in the top right corner. All of the other noble gases in that family will have a full outer energy level when they have 8 valence electrons. But since helium only has 1 energy level, and that energy level is filled up when it has 2 electrons, helium will achieve its stable octet when it has 2 valence electrons in the first energy level. So 2 electrons will be the number of dots always for helium. So where do the dots go? When you draw your dot model, your first 2 dots have to go together. You can either put them on the right, the left, the top, or the bottom. It really doesn't matter where you start, but they do have to be next to each other. And that's because those 2 electrons are going to exist in the same orbital of of a sublevel, and it's called the S sublevel. The next 3 dots you should space out separately. You can go top, left, bottom, like go around counterclockwise, or you can go clockwise and do like bottom, left, top. It doesn't matter as long as you're consistent with which way you go. The next 3 dots, you're going to go back and partner up those individual electrons. Again, either go counterclockwise or clockwise, stay consistent. The maximum number of electrons is 8. So these other 6 electrons that you've added in separate places, those represent electrons that are in the p sublevel, and it has 3 orbitals. And so the first 3 electrons you placed, you're individually placing an electron in one of each of the 3 p orbitals, and then when you go back, you're partnering them up. And we'll learn a little bit more about orbitals later on, and that will make more sense. Okay, I want to show you guys an example. So let's look at bromine. Okay, bromine, here's our periodic table, and I can see that it's got a Roman numeral VII, which is a 7. So it's going to have 7 valence electrons. So the first 2 dots are going to go together. I usually start on the right-hand side, but again, it doesn't matter. You could do top, left, or bottom. And then we're going to put our next 3 dots individually, and I'm going counterclockwise, top, left, bottom. And so far we have 1, 2, 3, 4. We have 5 valence electrons so far. We need 2 more to make 7. So those other 2 electrons get partnered up. Again, I'm going counterclockwise, so I add a partner to the top and a partner to the left. And notice there's a missing electron there at the bottom. Okay, so this electron in this very bottom spot, it would be a p sublevel, the 3rd orbital of the p sublevel. It doesn't have a partner. So that's an opportunity that atom would say, I kind of want to form a chemical bond. I would like to have an electron in that missing spot. Okay, couple weird things. Carbon just does its own thing. Carbon is the basis of all organic life. And the reason it's the basis of all organic life is because it is sort of amazing. It can kind of decide the best way to make things happen. So a lot of times carbon will actually make hybrid orbitals. And what that means is that it can form 4 bonds. It'll separate out those first 2 electrons. So we can draw the dot model for carbon as 4 individual dots, and it kind of shows the ability of carbon to make 4 bonds. So let's talk about ions. Okay, well, ions are atoms that have either gained electrons or lost electrons. So what happens for metals is that they always give away all of their valence electrons. And that's going to leave them underneath with a full outer energy level. So that's how they achieve their stable octet. Anions are formed by nonmetals, and they do the opposite. Okay, they will fill up enough electrons. They will take electrons away from other atoms in order to fill up their outer energy level and achieve their stable octet that way. And that means that your atom now has a charge. It's either gained electrons or lost electrons, so it's charged. And we always write the charge as a little superscript. And we refer to the atom now as not as an atom, now it's called an ion. Once it's charged, it's an ion. So how do we draw dot models for these ions? Well, for cations, we just take away all the electrons, all the valence electrons. We put brackets around it to remind ourselves, hey, this isn't an atom, this is an ion. And we write the charge in the top right corner. For anions, we fill up enough electrons to make 8, or in the case of helium, to make 2. Hydrogen and helium would be filled with 2. And then we, again, brackets, and we write the charge in the top right corner. So let's look at an example of each of those. Here's the dot model for calcium, normally as an ion with 2 valence electrons. Since calcium is a metal, it's going to form a cation, which means we remove those electrons. So that's going to look like this. Electrons gone. So it's going to give away those 2 electrons. Then we have to put brackets around it to remind ourselves, hey, that thing has lost some electrons. And then we put the charge to tell us how many electrons it's gained or lost on the outside. Since it lost 2 negatively charged electrons, losing electrons means it has extra protons. And since I lost 2 of them, that makes a 2+ charge. All right, let's look at an anion. So this is the bromine atom. We just did it a few minutes ago, and if you guys remember, it had 7 valence electrons, right? Because it's group 17. And so those are my 7 dots that represent the 7 valence electrons in bromine. Okay, how is it going to form an ion? Well, since it's a nonmetal, it's going to take in enough electrons to make 8. So I've added that extra dot in red there to make my 8th electron. Anions or nonmetals always form anions and fill up their dots. Okay, then I got to add brackets because it's an ion, not an atom. And I got to figure out the charge. So since it gained 1 electron, it gained something negative. The charge would be 1 minus. Now, you don't have to write ones as charges. They're understood. You can just write the plus, and everybody knows that that means 1. Okay, so we've looked at 2 examples. We looked at forming a cation, that was our calcium ion, and we've looked at forming an anion, that's our bromine ion. And one more thing about anions, okay? When you form an ion out of a nonmetal, the name of it changes a little bit. So we wouldn't call this the bromine ion. We actually changed the ending of the name of the nonmetal to ide, I-D-E. So this would be bromide. That's going to help us later on when we start naming chemical compounds. So for all those nonmetals, when they form ions, please remember to change the name of them to ide. So like chloride, iodide, fluoride, bromide. Thanks so much for joining me, and this has been the electron dot diagram presentation for atoms and ions.